Hello ladies and gentlemen, thanks for tuning in today again for what is the 10th lecture now of GGS 300, Quantitative Methods for Spatial Science. Today we're going to be focusing on multi-samples using something called analysis of variance. And I'm going to be presenting this lecture to you now, and then we're going to get into some lab work later on where we're going to work through the calculations in some R code. So before we begin, this is just to remind you that the assignment's due assignment 7 on the 30th of October, so I hope that that's now been submitted. We also have some tests coming up, so I'm going to test you on all of the work that we've essentially covered in the last 4 lectures and labs, and hopefully then that will prepare you for the upcoming midterm, which is going to be set in the next week essentially. So you'll hear more details about that in due course. If you've got any issues or queries, then please do reach out to me. So in this presentation today, we're going to focus on providing introduction to you on the analysis of variance, particularly in how you therefore test multi-sample data sets. You'll remember that in the first part of this course, this class, we've essentially focused on descriptive statistics, which enabled us to quantitatively understand data and to be able to kind of qualitatively draw conclusions about it from visualizing it, for example, looking at single statistics. Whereas in the second part, so what we've been doing recently, we've moved on to inferential statistics, and we're able to use more formalized quantitative methods to make statements about the data that we collect, essentially. Hopefully understand the world around us. So you remember last time that I brought up this concept of a flowchart for commonly used statistical tests, and we were focusing previously on paired t-tests and the Mann-Whitney U and Wilcoxon rank sum tests. And today we're moving on essentially to those cases where you have more than 2 groups, so 3 or more samples. And essentially we have the same approach again, which is, okay, are our data normally distributed? Do they conform to parametric assumptions? If they do, then we're able to use analysis of variance, as we're going to cover today as the first test. And if they don't, basically you have a non-parametric data test. So maybe the data don't conform to the assumptions, which include normally distributed data or equal population variance, and therefore we would potentially downgrade that data to ordinal and use a non-parametric test such as the Kruskal-Wallis test. So this is by no means comprehensive for every statistical test, but it just starts to give you a little bit of a flavor that we are addressing certain parts of the overall kind of landscape of statistical testing. And by the end of the course, hopefully you'll be pretty well geared as to understand the landscape, so that if you need to dip into any of these tests in the future, then you should be able to do that relatively easily. So let's get stuck in then. So first of all, we've talked about 1 and 2 sample tests in the previous lectures, but often we have more than 2, so we might want to compare differences between regions, continents, states, or maybe we've taken a bunch of samples from different parks, forests, different types of land covers, and therefore we want to understand if they all come from the same population, or maybe if they come from at least 2 different populations. So the logic behind these tests is essentially that if the multiple samples that you have are from the same population, then the sample means shouldn't differ. Okay, so there'll be some minor difference which you would expect to occur as a result of standard normal sampling. So you get some variation in there, but they're not significantly different. Whereas the other kind of logic, the other outcome that you might get essentially is that if the sample means differ by more than the variability which we would randomly expect to happen from just ordinary sampling, then we can reasonably conclude that the samples have been drawn from different populations, so at least 2 different populations, and that key phrase there will be important for you understanding these tests, and particularly as you move towards being examined. So it doesn't tell us how many different populations the samples may have been taken from. It just tells us that they may have been taken from at least 2 different populations, and I'll probably return to this to kind of drill this message home as we go through this lecture, but it's pretty important for your understanding. And I think that's because a lot of these tests obviously have limitations. So a key part of this class is that you're able to understand when you're presented with statistical data later in life, the shortcomings of particular tests, so that you can really kind of understand statistical data in a critical way. I mean, that's really the key point of this. So if we have tests with 3 or more samples, then we've got 2 different types of approaches. So we have a parametric analysis of variance, so ANOVA approach, which requires us to have continuous interval ratio data from a normal distribution. And then if our data unfortunately don't meet those that requirement, essentially, so those assumptions associated with that ANOVA test, which I'm going to go through in detail very shortly, then we would have to look at a non-parametric solution. So the Kruskal-Wallis allows us or enables us to basically carry out a similar procedure, but for ordinal data, essentially. So maybe we downgrade our interval ratio data into ordinal, so ordered categories, because ultimately we're not able to meet those other assumptions. So these are the 2 different approaches that we have depending on whether the data are parametric or non-parametric, and this is what we're going to cover today. So for these statistical distributions, both ANOVA and the Kruskal-Wallis test, the test statistic is always positive, so we can't use the Z or the T distributions because they can be negative, okay? So that you have a mean of 0 and the mean can either be positive or negative, so we need to take a different approach. So essentially in ANOVA we use the F statistic. So F is essentially the T distribution, but we square it so that it's always positive. And in the Kruskal-Wallis case we use the H statistic. So H is the chi-squared distribution, so this is essentially the normal distribution that's been squared again, so it's always positive. So you'll just need to learn those test statistics so that when we think about the test, you know exactly what we should be looking for. So the caveats are that the tests, as I mentioned before, are trying to show that not all the samples come from the same population. And we test whether at least one sample comes from a different population, but that doesn't mean that the test tells you how many different samples the populations could have come from. So it doesn't tell you how many samples are different, which ones are different. So these limitations are important, and hopefully now we've kind of gone over this, and we will go over the math in the rest of this lecture. When we move on to going through the lab work, and we can actually work through on a line-by-line basis, the math, hopefully then it's a lot clearer than it is now. So just before we begin and we get into the math, let's just focus quickly on visualizing the descriptive statistics, because if you have these samples that have come from, maybe you've been out and you've collected them. Here we just have high school graduation rates, essentially by state, grouped by region. You are able to visualize these. So we went over box plots previously when we focused on descriptive statistics, and one type of descriptive statistic approach which we didn't cover for visualization was notched box plots. But essentially, as you can see here, the notched box plot uses a narrowing of the box around the median. So can you see how this box narrows in the very center of this shape just here, representing the median line, so this thick black line here. And these notches are roughly equivalent to 95% confidence intervals. So they're quite useful as a descriptive pretest to help you understand if the samples may be potentially different. So if the notches don't all overlap, then this is a clue that at least one sample is not from the same population. So if we look at the box plot on the left-hand side here, we've got those regions, and we've got the high school graduation rate, and we have all of the state data helps us, all of the states in the Northeast help us develop this box plot just here. So that's your standard box plot. We're then able to look at what would happen if we used a notched box plot. So again, it's the same underlying data. So you've got all of the high school graduation rates by state, and then they're grouped based on their region. But the key point is that you can see that the actual notches for many of the samples just don't overlap. So that's an indication that the samples are potentially going to be from different populations. So you can see that the northeast and the north central are relatively similar, and there's quite a bit of overlap there. But then, in the south, we have particularly decreased, so lower high school graduation rates, which is obviously concerning. Whereas in the west, we have really quite higher high school graduation rates. So you can see already that potentially these data are going to be coming from different populations. So it's a bit of a litmus test as a first kind of port of call when you've got some data and you just want to kind of understand it before you start to actually run some formalized tests. So that's kind of an introduction. Now we're going to get into ANOVA, so analysis of variance for parametric data. So we have 3 different steps, and there are 6 required calculations in order to calculate ANOVA. I think that this is the clearest way to present it. When I first approached, teaching this, I was worried that you were going to get a bit swamped with all of the different calculations. So that's why I've actually broken it down into these 3 different steps with multiple different parts. And actually, I'm going to present it now in this order. And then when we get into the lab, I also present it in the same order in the code. So I'm hoping that you'll be able to simultaneously look here at the different steps and parts, and then see the calculations for yourself within the code. And then you'll be able to make comparisons between the math, the formalized math structure, and then the lines of code where we actually tap out those calculations. So first of all, we need to calculate the between group variability, which essentially involves calculating the total weighted mean of all the samples, the between group sum of squares, and the between group mean of squares. And then we need to calculate the within group variability. So this basically calculates the within group sum of squares and the within group. Sorry, there's a mistake just there. Let me just change this on the slides. There we go. The within group sum of squares. And then finally in step 3, we need to calculate the test statistic. Okay, so I hope that that's clear for you. So what we need to do is make sure that the data that we've got actually fits the assumptions for ANOVA. So the objective is to compare the means of 3 or more independent random samples. So we need to have, as a first point of call, 3 or more random samples. They need to be independent samples so that we don't have things like correlated errors. And we need to make sure that each population is normally distributed and the populations have equal variance. And as I mentioned before, this particular test requires continuous, interval, or ratio sampled data. So once we know we met those assumptions, we can then think about our hypotheses. So the null hypothesis essentially is that the means from each of the different samples are broadly equal to each other. So you can see here mu1 is equal to mu2, mu2 is equal to mu3, so on and so on and so forth. So that's the null hypothesis, where we don't expect any significant difference other than the difference that might occur just by random sampling. In the alternative hypothesis case, so HA here, we expect that the mean of the samples are significantly different, and they differ by more than the type of variation that you would expect to just occur through random sampling. So mu1 is not equal to mu2, mu2 is not equal to mu3, so on and so forth. So now we've stated the hypotheses, we need to remember that the test statistic for ANOVA is the F test, the F statistic. So that's what we need to obtain essentially. And part 3, you'll remember, is to calculate the F test statistic. And to do that, we basically need to make sure that we've got the between group variability, MSB, and the within group variability calculated in the other 2 steps, the other 2 parts that we're about to go over. Okay, so within ANOVA, a sample is also called a group. Okay, so we might have lots of different samples of house prices that we pull from different places. In ANOVA, that sample term is also interchangeably used for groups, so I just don't want you to be confused if you see that written in the book or elsewhere. The within group variability, so MSW, is essentially the total of all of the sample variances. So that was the denominator that we have down here in this equation. Whereas the between group variability, MSB, which was the numerator in that equation, is essentially the variance of the sample means among the different groups. So if the samples are from the same population, ideally we would expect there to just be a very small amount of variability between the groups, maybe even zero. Whereas in contrast, if we thought that the samples were going to come from at least two different populations, then we would expect that the between group variability would be quite significantly larger. Okay, and now I've qualitatively stated that logic for these tests a couple of times, so what does that mean in reality? Well, let's think of it in terms of, imagine we have the null hypothesis here. The null hypothesis assumes obviously that the samples are equal to each other, so imagine that the samples all come from a set of distributions overlapped like this, where the means are essentially in the same place. And that contrasts with the alternative hypothesis over here that we see, where imagine that the sample means here for sample 1, sample 2, sample 3 are significantly different in their size. So imagine that you have quite substantial differences between these means. In the case 1 that we have just here, we can see there's very small differences between these means here, so you might not have enough evidence in that case to reject the null hypothesis. Whereas down here on case 2, we've got quite a substantial amount of difference between the sampling means, so you probably would have quite enough evidence there to reject the null hypothesis and accept the alternative hypothesis. Okay. So how do we do those actual calculations? So for step 1, we want to calculate the between group variability. So in part 1, we need to make sure that we obtain the total weighted mean of all samples. So we have the mean of each of the samples, so x bar I here. We have the number of observations in each of the samples, so for sample 1, sample 2, sample 3. And then we have the number of groups, so the number of samples that we have overall, essentially. And then we have the total number of observations in all of the sample. And we're able to get x bar t here by just following through this equation, so calculating the numerator and then calculating making sure we divide it by the denominator. And then once we've got x bar t here, so we'll do this calculation later on a step-by-step basis, we're able to take it through down into part 2, so you can see the x bar t just here. In part 2, we're then going to calculate the between group sum of squares. So when we say between group, think of this as the variability of the difference between the different samples. So this distance here, where we've got the red the red arrows. So we're thinking of how far away potentially the sample means are from each other. And we're able to get the between group sum of squares by working through this particular equation here to get SSB, and then we're able to take the mean of the squares, so essentially by taking the SSB as the numerator here, dividing it by, so k is the number of groups minus 1, so it gives us the number of degrees of freedom, and then that provides us with this, this between group mean squared value just here for part 3. So now let's move on to step 2. So in step 2 we are calculating the within group variability now. So we're interested in calculating the within group sum of squares first. So what we need to do basically is find the sum of squares here for the within group metric, so SSW. And essentially we're able to do that by using the variance of each of the samples. So we'll calculate this by hand once we get through to the lecture. And then we're able to take forward the SSW parameter that we calculate in this equation as the numerator into part 2, which focuses on calculating the within group mean squares. And what we do is we divide it by the denominator here, which is so the number of total observations minus the number of group samples that we have. And then that produces this MSW. And then when we've done that, we're able to take the results of step 1 and the results of step 2 and get our F-test statistic. So you remember here we got the between group mean squares value. So the end of step 1 part 3, that forms the numerator here, and then we're able to, for step 2 part 2, take the MSW value that we get and use that as the denominator, and that provides us with the F-test statistic. So just think of the within group variability that we've calculated here in step 2 as the difference within each sample. Okay, so ANOVA can be summarized in an ANOVA table. So what we have here are rows for the between group and within group metrics and for the totals, and then we have columns for the source of variation, the sum of the squares, the number of degrees of freedom, the mean of the squares, and then the F ratio and the p-value. Okay, so hopefully these then correspond to those previous steps that we carried out. So in the first step, you'll remember that we calculated the between group variability. So it's this row just here. We calculated the sum of squares, the number of degrees of freedom, and the mean squares. With the within group variation, we calculated in step 2 just here. So we calculated the sum of the squares, the number of degrees of freedom, and we got the mean squares for the within group variation. And then essentially in step 3 just here, we got the F ratio by being able to divide MSB by MSW. And then when we get that statistic, we're able to then estimate the p-value for it. So just running along here, we will return to the example of high school graduation rates by US region. We have all of the high school graduation rates for each of the regions, and you can see that we get an F value down here of 38.57, which actually yields a p-value of very, very highly significant p-value of 1.3 to the minus 12. So that's telling you that there's a very, very high degree of certainty that the samples that we've taken come from at least 2 different populations. Okay. Okay, so that was ANOVA, analysis of variance, which obviously we do if we've got parametric data. If in the case, which is pretty common, we don't have parametric data, then we would opt for a non-parametric test. So at least from the work that I've done, I mean, I would struggle to name a time when we have actually had data which is normally distributed. Quite often when you're collecting data, maybe your distribution's truncated, maybe it's just a completely different shape, like we covered with the income distribution that we went over in the first and second classes. And therefore, you just might not be able to meet those assumptions for using the parametric tests, which is completely fine. It means that we have to use a non-parametric approach, which means there will be some loss of information because we'll have to downgrade that interval ratio data into ordinal data. So there's a loss of information there, but I think when I was starting out working on statistics, I was thinking that it was almost bad to use non-parametric data, that the data is almost faulty, and that's just not a very good way to approach this and think about this. You need to use the right test for which you are able to adhere to the assumptions that the test requires, because as I mentioned before, people can disagree with your results and your interpretation of the results, but what you always want to be completely rigorous on is your method. If you have a strong method, then people can disagree with the results, and that's fine. What you don't want is for people to say that you've used an incorrect method, and therefore the results that you've produced are essentially junk results. That's the worst possible outcome that you can have as an academic or in a professional career. So it's really important that you pay attention to these different assumptions. So what are we going to do with the Kruskal-Wallis test? Well, we're going to be comparing the mean ranks of 3 or more independent random samples for difference. Those assumptions I just mentioned are going to focus on the fact that we do actually have 3 or more random samples. The samples are actually independent, so we don't have correlated errors between them. The populations are actually non-parametric, well, they can be non-parametric, and the fact that the data are essentially ordinal observations, so that may be downgraded data. And what essentially we then do is we need to state our null hypothesis and alternative hypothesis. So in the null hypothesis case, the populations have just been drawn from the same population essentially, so there would be no difference in the samples that we get. Whereas in the alternative case, the populations are seen to basically be non-identical, so they've potentially been drawn from different populations. And the test statistic, as you will remember, is the H test statistic, so the Kruskal-Wallis H test statistic. And we're able to calculate the H using one of these equations just here. So this one up here actually contains correction factor, essentially for ties. So when your data are ranked and there are ties between them, you may need to use this one when you've got more than 25% of your data being tied. And then we've got the normal calculation just down here. So essentially, what you need to do is make sure that you've got the correct values to input into these calculations. So Ni is the number of observations in sample I. N is the total number of observations in all of the samples that you've got, so the total number of K samples. Ri is the sum of the ranks in sample I, just here. G is the number of groupings of different tied ranks. So G is just here in the denominator. And Ti is the number of tied values within group I. Okay, so we'll work through this later in the laboratory session. You'll remember from the last class when we used the Wilcoxon tests, we went through a very similar method to this. So for the Kruskal-Wallis test, by hand, what you need to do is you need to basically combine all of the observations which you've gathered from the K samples into a single list, right? Hopefully that is you can remember that we use a very similar method in the previous week, so this is familiar to you. Then we need to basically sort the observations and rank them based on their position within the overall distribution. When two or more of the values are tied, we need to basically use the average rank, which is assigned to each of those positions. And the ranks for each of the samples are then basically summed, so we get the summation of those ranks. And then we can calculate the H value, obtain the P value using the R function, PCHISQ, which essentially is the chi-squared distribution. So if we just look at that here, this is the non-central chi-squared distribution that we're able to use here, and we're able to get quantile values, for example, like we did previously. So hopefully part of that test is somewhat familiar to you. Ultimately, this is an extension of the Wilcoxon test. So we'll remember that both of them are non-parametric. So conclusions are regarding the mean ranks and not arithmetic means. We would expect, as stated in the null hypothesis, that each group has roughly the same average rank. But that if there are patterns, then essentially we would reject the null hypothesis if we felt that the samples were being pulled from different populations. We had enough convincing evidence to reject the null hypothesis. And again, the notch box plot is not a bad place to start when you're kind of understanding the data and you want to understand where the different groups are positioned. So this is just an example here of how you can get the Kruskal-Wallis chi-squared value, 36.15, for the high school graduation by region data. So we have 3 degrees of freedom, but we had a highly significant p-value when running this test, so 6.953 to the minus 8. So it's very, very significant. So here we would have enough evidence to reject the null hypothesis at the 95% level, for example, because it's significantly below 0.05. So that alpha value that we have as the point at which we are confident that we have enough evidence that we can reject the null. So this is the end of the lecture for today. It is also the last lecture at the end of the second part of the course, essentially. So there's going to be an upcoming midterm exam, which is going to cover all of what we covered in the second unit. I think I mentioned at the beginning that I would be testing in the next week, basically. So these are ungraded tests, and I'm basically going to be setting you a bunch of work to gear you up for the midterm exam so that you're fully prepared. So please make sure that you cover the tests that I do set, and then hopefully you're in a really good, strong position in order to really excel on the second midterm. Fantastic. Well, thank you all very much for tuning in today. I hope you have a good day. I look forward to seeing you again in the lab session, and good luck with the content. Thank you. Goodbye.